So welcome to today's webinar on simulation-driven design and casting with Altair Inspire. Myself and Cheryl Snedden will be your host for this session. Whether you're an engineer, designer or a manufacturer, hopefully this webinar will provide you valuable insights into leveraging simulation-driven design to optimize workflows, reduce costs and enhance product quality. A little bit on why this topic matters and why it matters for Symmetry. So manufacturing is evolving rapidly, and simulation-driven design has become a game changer in product development. By integrating simulation early in the design process, companies can minimize prototyping costs, reduce production errors, and accelerate time to market. When applied to casting, this approach helps predict material flow, cooling patterns, and potential defects, allowing for smarter design decisions before production even begins. So we've designed this webinar for engineers and designers looking to enhance their design validation process, manufacturing professionals focused on optimizing casting workflows, product development teams aiming to improve efficiency and reduce material waste, and anybody interested in leveraging simulation technology for better design outcomes. So quick introduction to Cheryl and myself. Cheryl is based in Scotland. She's been working with Symmetry for over 10 years, and she has previous experience as a mechanical designer in the oil and gas industry. And myself, I'm based in the Midlands. Historically, I'm a toolmaker by trade with experience in CAD/CAM, and more recently, simulation of manufacturing processes and also additive manufacturing in the polymer industry. So a quick overview of the table of contents for today's webinar. So the fundamentals of simulation-driven design and its impact on modern engineering, an introduction into Altair Inspire, which is a powerful simulation platform for product development, and a deep dive into the casting process and how simulation can help predict defects, improve efficiency, and optimize manufacturing outcomes. And then at the end, we will have a Q&A session where we can answer all of your questions and provide further insights. Just as a side note, we encourage you to be interactive during this session, so feel free to drop any questions in the chat, and we'll address them during the Q&A segment. So before we dive into the technical aspects of simulation-driven design and manufacturing, and before we show you Inspire Cast, I'd just like to show you some of the key challenges that engineers and manufacturers face when designing innovative products. Designing and manufacturing successful products isn't just about creating something that works, it's about optimizing for performance, sustainability, and affordability. These are the three factors that are crucial in today's competitive and fast-paced market. So for design for performance, this is at the heart of the product development. Whether we're designing automotive components, industrial machinery, or consumer products, we need to ensure that we've got strength. The product must be durable and capable of withstanding real-world conditions. Speed, this is efficiency and efficient production and reduced time to market, which is critical. And quality, the final product should meet industry standards and customer expectations. So designing for sustainability, sustainability is no longer optional, it's a necessity. With increasing regulations and customer demand for eco-friendly products, companies must consider new materials, exploring lightweighting, recyclability, and also introducing bio-based materials to reduce, reuse, and recycle, minimizing waste through the product life cycle. This is where simulation comes in. It can help us analyze the environmental impact of different materials and design choices, enabling us to make more sustainable decisions. And design for affordability. Cost is always a major factor in product success, so we need to design products that are not only functional and sustainable, but also are economically viable. And this means controlling production costs, optimizing the manufacturing process to reduce waste and improve efficiency, reducing maintenance and warranty costs, so designing products that are reliable and require minimal maintenance. Simulation is great because it can help us predict potential failure points and identify areas for improvement, leading to a more cost-effective design scenario. As we move forward, we'll see how simulation-driven design, powered by tools like Altair Inspire, can help us address these challenges and create innovative products that are not only successful, but are also sustainable and affordable. Here's a concrete example of how simulation-driven design can be applied to address the challenges that we've discussed. This is an example of a battery electric vehicle. These present unique engineering challenges that require a multidisciplinary approach. Simulation plays a crucial role in optimizing various aspects of the vehicle, from its core components to its overall performance. So the electric motor design. This simulation helps optimize the design of electric motor for maximum efficiency, power density, and torque. PCB design, where thermal management is critical for battery packs and electronics. Simulation helps us ensure optimal cooling and preventing of overheating. Control systems, so simulation allows for the development and testing of advanced control algorithms for battery management, motor control, and vehicle dynamics. Probably a more important one is lightweighting. Simulation enables the analysis of different materials, structural designs to minimize weight while maintaining structural integrity and safety. Aerodynamics. So the simulation of aerodynamics helps us optimize vehicle aerodynamics to reduce drag and improve range. NVH and control simulation predicts noise, vibration, and harshness levels within the vehicle, ensuring a comfortable and quiet ride experience. Motion dynamics. This is where simulation is used to analyze vehicle dynamics, including handling, stability, and ride comfort to ensure a safe and enjoyable driving experience. And probably more recently important is connectivity simulation, which helps evaluate the performance of communication systems and ensures reliable connectivity for advanced features like autonomous driving, for example. So by leveraging simulation at every stage of the development process, engineers can make more informed decisions, optimize performance, and accelerate time to market. So looking at how simulation-driven design is integrated into a product development workflow using Altair Inspire Cast, for example, we've got generative design, and this is where the design process starts. Generative design algorithms explore a vast design space to find optimal solutions that meet performance, sustainability, and manufacturing constraints. Inspire's generative design tools allow engineers to define performance, objectives, and constraints, and then the software generates a range of innovative design concepts. Performance analysis for both structures and fluids. Once initial design concepts are generated, structural simulations are performed to evaluate the performance under variable loads and conditions. Inspire's structural analysis capabilities enable engineers to predict stress, strain, and deformation, ensuring the design meets strength and durability requirements. And the same applies for fluids. For any applications involving fluid flow, such as aerodynamics or fluid cooling, Inspire's CFD or computational fluid dynamics tools are used to analyze fluid behavior, and this helps us optimize designs for factors like drag, lift, or heat transfer. For dynamic motion, as we mentioned in the previous slide, for moving parts and mechanisms, dynamic motion simulation are conducted to analyze factors like kinematics, forces, and vibrations. And these simulation capabilities help ensure smooth and efficient operation of moving components. And finally, the manufacturing process, and in today's webinar, we'll demonstrate our casting capabilities, but simulation is used to assess the manufacturability of the design, and Inspire's manufacturing process simulation tools help us predict potential issues such as casting defects, tool wear, and assembly challenges, enabling proactive design adjustments. I guess the key benefits of this workflow is that we can improve product performance by integrating simulation throughout the design process. Engineers can create products that perform better and meet demanding requirements. Reducing the development time. Simulation definitely helps identify and address design issues early on, reducing the need for costly prototypes and costly iterations. And enhanced collaboration between teams. So Inspire's collaborative environment enables seamless communication and data sharing amongst these design teams. And rapid convergence. The iterative nature of workflows allows us to quickly evaluate designs and rapid conversion of optimal solutions, all in a digital environment. Again, coming back to this, reducing the time development. Some of the key manufacturing methods and how simulation can be used to address their unique challenges within the Inspire portfolio. Today we'll talk about casting, and casting simulation is used to predict material flow, identify potential defects like porosity and shrinkage, and optimize gating and venting systems for better casting quality. For metal forming, simulation helps analyze the forming process, predict material flow, and identify potential issues like springback and wrinkling, leading to improved tool design and reduced scrap rates. For injection molding, you can predict filling patterns, cooling times, potential defects like sink marks and warpage. This enables the optimization of the mold design and the process parameters, as well as the part design. Extrusion simulation can help analyze the extrusion process, predict material flow and pressure distribution, and optimize die design for improved quality products and reduced defects. Additive manufacturing simulation plays a crucial role in optimizing the process for additive manufacturing by predicting build orientation, support structures, and potential defects like warping and cracking. And last is polyurethane foaming. Simulation in this process can be used to predict foam expansion, cell structure, material properties, enabling optimization of the foaming process, but ultimately achieving desired product characteristics. So some key benefits of this simulation-driven design process is reducing prototype and testing costs, improved product quality, faster time to market, and increased efficiencies. Here's an example of how simulation-driven design can be applied to a real-world engineering challenge. In this example, this is a design of a suspension bracket that is both lightweight and strong enough to withstand the dynamic load experiences during motorcycle riding. Optimizing the design for manufacturing process is also cost-effective. So physics-based generative design. So we start by using design algorithms within Inspire to explore a wide range of possible bracket geometries. These algorithms consider performance objectives such as strength and stiffness, as well as manufacturing constraints and material properties. The dynamic motion analysis is used to simulate the loading conditions experienced by the bracket, providing realistic inputs for the generative design process. Next, we evaluate the manufacturing process. Once we've got a promising design and the concept is generated, Inspire simulation tools are used to evaluate their manufacturability. So, for example, we can simulate the casting process to predict potential defects like porosity and shrinkage, and optimize the gating and venting systems for better casting quality. This early evaluation helps us identify potential manufacturing challenges and allows us to design adjustments to improve manufacturability and reduce costs. So this enables innovation really within the platform. So by leveraging simulation and AI-driven solutions, we can explore more innovative and advanced designs that would be difficult to achieve through traditional methods. So this enables us to create lighter, stronger, and more cost-effective suspension brackets in this example, leading to improved motorcycle performance and handling, which was the key objective. And the benefits of this approach, again, is to reduce development time. By simulating the entire design and manufacturing process, we can identify and address potential issues early on, reducing the need for costly prototypes and those costly iterations that are associated to them. Improved product performance. So the optimized design results in a lighter and stronger bracket, enhancing motorcycle performance and handling, and increased efficiency. So the streamlined design and manufacturing process leads to reduced material waste, improved resource utilization, and ultimately faster time to market. Which brings us on to Altair's Inspire Cast, and more sort of focused on the cast manufacturing process. So within Inspire Cast, this is a comprehensive simulation-driven design environment. Inspire Cast provides a comprehensive environment for the simulation of metal casting processes. It integrates all the necessary tools to design, analysis, and optimization of the casting process within a single user interface, which is very user-friendly. It's fast, it's easy, it's accurate, and it's affordable. Inspire Cast offers a fast and efficient workflow for the casting simulation, making it easy to perform easy and early feasibility studies and develop optimized casting processes. The software is designed to be easy to use, requiring minimal training, and offers an affordable solution for businesses of all sizes. There is a 5-step process to optimization, and Inspire Cast guides users through a 5-step process to develop a complete casting simulation project. The structured approach ensures that all critical aspects of the casting process are considered and optimized. So, by leveraging Inspire Cast, companies can reduce prototyping and testing costs, improve product quality and consistency. They can accelerate their time to market, but ultimately gain a competitive edge in the marketplace. So this comprehensive coverage allows for accurate simulation optimization across various casting manufacturing scenarios. This slide just highlights some of the supported processes that we can do today. So gravity casting is the most common and most cost-effective method, where molten metal is poured into a mold under the influence of gravity. Inspire Cast can simulate filling patterns, solidification, and stress analysis for gravity casting. Next, we've got high pressure die casting. So this process uses high pressure to inject molten metal into a die cavity, resulting in high quality and complex parts. Inspire Cast can simulate filling, solidification, and stress analysis for high pressure die casting. And this takes into consideration the effects of high injection pressure. Next is low pressure die casting. In this process, molten metal is forced into the die cavity by gas. Inspire Cast can simulate the filling process, solidification, and stress analysis for low pressure die casting, taking into account the influence of gas pressure. Investment casting, which is also known as lost wax casting. This process involves creating a wax pattern that is then coated with a refractory material and melted out, leaving a mold cavity. Inspire Cast can simulate the filling, solidification, and stress analysis for investment casting. It also considers the influence of the mold material and the process parameters. And then last, we've got tilt pour casting. This involves tilting the mold to control the flow of molten metal. Inspire Cast can simulate the filling process, solidification, and stress analysis for this pour tilting casting process, considering the effects of mold tilting and metal flow dynamics. So by covering a wide range of casting processes, Inspire Cast provides a versatile and powerful tool for engineers and manufacturers to optimize their casting operations and improve product quality. So just before I hand over to Cheryl to sort of show you the software live, to give you an overview of some geometry creation capabilities. It's an intuitive interface. It's one-click geometry generation for cores and molds in the casting process. Auto creation of risers with full control of all-screen manipulation of size, and guided templates for most of the casting process simulation. The focus in Inspire Cast is a 5-step simulation setup that Cheryl will demonstrate in a moment. Number 1, we import and create the geometry. 2, define the gates, or we can import and create components, set up the process, and then quite simply run and analyze the results. One of the important things about simulation is being able to visualize results and interpret those results to create a solution. And Cheryl will give you a quick overview of how we achieve that.
Thanks, Neil.
I just got one more slide, actually.
No worries.
That's fine, yeah. So just an overview then of Inspire Cast. It's fast and robust for the metal casting solution. It's unique and it's powerful geometry-based user interface for the filling, cooling, cycling and warpage stage. So I'll hand over to Cheryl to give you the product demo.
Morning, everyone.
And let me know when.
Yeah, I mean, Neil, I think you can just start. I think most of the information that you've given us was spot on anyway. So guys, just to let you know, this demonstration here is some parts that have been imported in. Now the geometry is not overly complex, but you can see the centre part, and then the other parts that have been modelled in are more gates or airways. So these are the 5 steps that we take through the casting process. So you can see in the icons above, just the 5 steps that we take. Very simple. First thing we do is we pick the material of the part. So you can see there's a list of different styles of materials that we can choose throughout the process, and we can adjust the parameters of those as we need to. So once we've addressed that, we can start to address the filling system. So how it's going to be filled. Do we need, there can be one gate or multiple gates in as we fill. And then we're going to apply gravity in the direction of the process. So we need to tell it what direction the gravity is in as the molten material is pushed through in to create the part. So once we create gravity, the next thing we're going to address is the gates. So you can see here we select the position of the gate. We can put in parameters and attributes about the start and the end of that process, and we can have multiple gates, like I say, but we specify the gate, and then we look at the components. There's lots of different ways we can look at things like sleeves. We can look at cooler systems, shot sleeves. In this instance, we're going to look at overflow. So we've got these overflow geometry areas around the part to allow us to make sure that we're creating a part that's sufficient and less errors. So we're going to apply the mould here as well. Again, we have different materials for the mould, have different attributes and properties, directions, size of the mould. And once we apply the mould, we can actually just turn it off. We don't need to see it in this process just now. We're just hiding that from the part tree. And then we're going to look at the process for high pressure. So you can see we've got gravity process, basic and low pressure in there as well. We're going to look at high pressure die casting. So we're going to put in some information about the initial phase and the second phase. Now these are velocities that you imply during the process. Now when we're looking at a velocity, we're looking at the low velocity is the initial avoidance of turbulence, and then the second velocity is more the molten injection, which is a quicker process through, and that's how we set that up through the process. As I said, it's really quick now. We can look at the results in terms of setting them up. We can look at things like adjusting the name, average thickness of the part, or the element size. We can then look at running the fill analysis with solidification. When we run the process, depending on the size of the part, it can take time. In this instance here, it doesn't take us too much time with this part. And then we start to look at the results. Now, the results themselves are based on fill time, temperature, and velocity. So we can look at things where the fill time shows the time that it takes for the material to reach areas of the part. And the temperature shows us the degree and the temperature during solidification. So when we adjust the legend on the right-hand side, we can use animation tools to animate how it would fill and how it goes into all of those extra overflow areas that we've modelled into the part. So we can see it as it slowly moves its way through, and we can adjust the overflow if needed. Now, Inspire is a full CAD application as well that allows you to adjust the geometry during this process, so we can reanalyze. So we look at the flow through the front, and we can see where it lands last. So you can see there might be some air trapped into that one overflow area. And we can look at that in a bit more detail in a different style of the Analysis Explorer. So you can see here the red areas are actually physically showing the last air of when the material was pushed through into the die. So we can readjust if there's too much of that in the model. We can readjust the model and also readjust the overflow areas. Then we can look at thermomechanical. Now, thermomechanical is coupled. It's a coupled fill-in thermo evaluation with deformation and contraction in the material, and we can look at that with velocity. So we can look at that as velocities of turbulence as the part goes around certain areas, and we can look at that with displacement. So that gives us an idea of how it will flow around those areas and how it will be turbulent in those areas. And again, we can adjust the design as suits. The other thing we can do is we can look at things like a percentage of that deformation as the mould is created. So we can scale that deformation and we can adjust to suit. So lots of things that we can analyse within the system. The main points that Neil was speaking about earlier on is obviously we want to capture any problems within the process before we do the process manually. So it's about those 5 steps that we take through. And as you can see, for anyone who's on the call who's a designer who might not have used any of the casting products before in the past, it really can give you results in a quick sense using those 5 steps. Thanks, Neil.
Thanks, Cheryl. So hopefully that gives you a quick overview of how quick and easy it is to achieve within Inspire Cast. Just before I open the floor to any questions that we can provide answers to, I've got a couple of case studies. There are lots of case studies to show you, so I've just picked 2. Amprove utilized generative design within the Altair suite, Altair Inspire suite. And the advantage of this is that they could carry out that iterative loop in the digital space rather than using physical prototypes, which is costly and is to be quite honest, is a waste of material. And another example for a major automotive manufacturer using high pressure die casting. This enabled them to create solutions for complex components. And ultimately, as Cheryl touched on in the demonstration there, also a well-designed gating system, which was crucial for delivering the optimum material flow and minimizing turbulence, which are critical factors for high pressure die casting. So from me, I think that gives you, hopefully that gives you a good overview of what Altair Inspire Cast and the Altair simulation driven design methodologies can improve for design engineers, for project engineers, and for the manufacturing process. So with that, I don't know, Jess, if there's any questions.
No questions at the moment, but if anybody wants to put anything in the chat, feel free.
So no questions there, I don't think. If you think of any questions in the future, feel free to reach out to us. We're always available to provide answers to those questions, and also to, if you want a further demonstration or an overview of how the methodology works, then please feel free to get in touch. Well, thank you very much for attending. On behalf of Cheryl and myself, hopefully that provided you with a good insight into the methodology of simulation-driven design, and have a great day.